Hello viewers. In this chapter, we are going to discuss friction and related physical quantities. We often see when we push an object, it covers some distance and then stops. Apparently, this observation is not following Newton's first law of motion. So, what is wrong in it? When an object moves over the surface of another object, its motion is always opposed by a retarding force. This means when the object was trying to move in the forward direction with a constant velocity, it is actually experiencing a retarding force opposing its motion. This opposing force ultimately makes the object to be at rest. This opposing force is termed friction. Hence, friction is an opposing force that comes into play when one body moves or attempts to move over the surface of another body. The frictional force always acts parallel to the surface in contact. Friction is a complicated phenomenon. Many aspects of friction are still not understood and explained properly. We have tried to explain friction based on observations only. To explain the roots of friction, various models were proposed. In the first model, it is said that every object is having irregularities on its surfaces. These irregularities are in the form of projections and depressions. When two surfaces come in contact, these irregularities get interlocked and opposes the relative motion. Once sliding has begun, the surfaces do not get enough time to settle down over each other completely. Hence, with this model, we can also explain why static friction is having higher values than kinetic friction. We will discuss more on static and kinetic friction in a moment. This model is having some drawbacks. According to this model, more the surface area of contact, more should be the presence of irregularities, hence more should be the frictional value. Again, if surfaces are polished, then according to this model, frictional values must reduce. In both cases, experimental observations are not supporting the above statements. It is observed experimentally that the frictional force is independent of the contact surface, and for highly polished surfaces, frictional value often increases. In the next model, it is said that frictional force arises due to the atomic and molecular forces of attraction between the two surfaces of their actual contact. On the microscopic level, every surface is having roughness. Therefore, when two surfaces are put together, the actual area of the contact is very much less than the apparent area of contact. At this point of actual contact, the pressure is very high, which helps in forming tiny wells. So, whenever we need to move one object over another, we have to break these wells first, which explains why frictional force is always opposing the motion. When the apparent area of contact is decreased, the number of contact points decreases. Since the weight of the body is not changed, there is increased pressure at the contact point. As a result, contact points flatten so that at the total contact area, pressure returns to their original values. This explains why the force of friction is independent of the area of contact of the surfaces. The actual area of contact between two surfaces depends upon the force with which the surfaces are pushed together, or the actual area of contact depends upon the normal force exerted by the supporting surface on the body. This explains why the force of friction is dependent on normal reaction. Overall, the second model is able to explain the frictional force in a better manner. There are two common types of friction, static and kinetic friction. The opposing force that comes into play when an object does not move over the surface of another, even though the force is applied to make it move, is called static friction. Kinetic friction is the opposing force that comes into play when one body moves over the surface of another body. When the force of friction is plotted against the applied force, the plot looks like the plot shown in the figure. In the plot, up to a critical force, frictional force and the applied force are equal in magnitude, and once applied force overcomes this critical value, the object starts to move. While the object is moving, the frictional force is constant and it is slightly less than the critical frictional force. If the object is at rest, then the referred frictional force is arising due to static friction, and once the object starts to move, the referred frictional force is arising due to kinetic friction. In the static friction region, the frictional force is always equal and opposite to the applied force. This is why friction is often called a self-adjusting force until it surpasses the threshold of the motion. Now, kinetic friction can be of two types: sliding friction and rolling friction. Based on the experimental observations, a set of rules can be framed which is very helpful for explaining friction. At first, the frictional force, static as well as kinetic, depends upon the nature of the two surfaces in contact and their state of roughness. Then, the frictional force, again for static as well as kinetic frictions, always acts parallel to the surface in contact and its direction is opposite to motion or attempted motion. Then, the frictional force is independent of area of contact between the two surfaces. Then, the magnitude of frictional force for static as well as kinetic friction is directly proportional to the perpendicular force termed normal reaction between the two surfaces in contact. Finally, in the case of kinetic friction only, the frictional force is independent of the speed of one surface relative to the another surface. Now we are going to discuss the magnitude of limiting friction. Consider a block of mass m lying on a horizontal surface. The normal reaction is the perpendicular force exerted by the surface on the block is R equal to mg. If Fc is the limiting friction, that is maximum static friction, then according to the laws of friction, Fc is directly proportional to the normal reaction, that is R. To replace the proportionality with equality, we have to bring a proportionality constant, which is μs. This μs is termed as coefficient of static friction. Therefore, the coefficient of static friction between two surfaces in contact, which is equal to the ratio of limiting friction and the normal reaction. In this case, the value of limiting friction will be μs mg. If the mass of the object is doubled, then the normal reaction will be doubled too. This in turn will affect the value of limiting friction. From the diagram, we can find that in this case the limiting friction will be twice of μs mg. In case the object is placed on an inclined plane, the normal reaction will be R equal to mg cos theta. Therefore, the limiting friction for this example will be Fc equal to μs mg cos theta. At next, we are going to discuss kinetic friction. If the object is moving with some velocity, then the friction applied on the object will be kinetic friction. From the laws of friction, Fk will be directly proportional to R. To replace the proportionality with equality, we again have to introduce one proportionality constant. This proportionality constant is known as coefficient of kinetic friction and we denote it by μk. Therefore, the coefficient of kinetic friction between two surfaces in contact is equal to the ratio of kinetic friction and normal reaction. For a given pair of surfaces, μk is always less than μs. Both μk and μs are ratio of forces. Hence, they are dimensionless physical quantities. At next, we are going to discuss the angle of friction. The angle which the resultant of the limiting friction and the normal reaction makes with the normal reaction is called the angle of friction. If alpha be the angle of friction, then from the diagram we can say tan alpha equal to Fc by R. Simplifying, we can write down tan alpha will be equal to μs. Therefore, the coefficient of static friction is equal to the tangent of the angle of friction. Now let us discuss how can we measure the coefficient of static and kinetic friction experimentally. We can measure the coefficients of static and kinetic friction for two surfaces simply by placing a block on a plane surface and incline the plane until the block begins to slide. For the measurement of the coefficient of static friction, let us consider a block of mass m is placed on a plane surface. If the plane surface is inclined gradually, eventually a point is reached when the block just begins to slide. Let theta c be the critical angle at which the sliding starts. In that condition, the block will undergo the forces due to its mass and limiting friction. In the figure, these forces are shown and they are also resolved into components. At equilibrium, we can write R minus mg cos theta c is equal to 0 by equating the components perpendicular to the inclined plane. Again, fc minus mg sin theta c is equal to 0 by equating the components parallel to the inclined plane. With simple mathematical steps, we can evaluate the coefficient of static friction from the above equation. This theta c is termed as angle of repose. It is the angle of an inclined plane at which a body placed on it just begins to slide. We can also see alpha is equal to theta c, that is, angle of friction is equal to angle of repose. When the angle of inclination is more than the angle of repose, the object placed on the inclined plane will start to slide down, overcoming the static friction. In this case, kinetic friction is working on the object. If we consider that the object is moving with uniform acceleration a along the inclined plane, then we can write down mg sin theta minus fk is equal to ma by equating the components parallel to the inclined plane. Again, fk is equal to mu kr, which is equal to mu k mg cos theta. From these equations, we can obtain the value of mu k. In case mu k is known to us and the acceleration of the block is unknown, we can even calculate the acceleration of the block too using this set of equations. If the angle of inclination is less than the angle of repose, in that case, the block will stay at its own position. And to move the block in upward or downward direction, we have to apply external forces on the block. We can estimate the minimum amount of force required to move the block either in upward or in downward direction, where we can see instead of considering coefficient of static friction, we have to consider coefficient of kinetic friction for the measurement of the minimum force required for the movement of the block. It is because if the block starts to move, the friction involved becomes kinetic friction. At first, let us consider the block is moving downward. Here, the frictional force and the component of weight are in opposite direction. Equating the horizontal components and performing simple mathematical steps, we can find an expression for the minimum force required for downward movement. Next, let us consider the block is moving upward. Here, the frictional force and the component of weight are in the same direction. Equating the horizontal components and performing the simple mathematical steps, we can again find an expression for the minimum force required for an upward movement. Now let us discuss rolling friction briefly. When one body rolls over another, the resistance offered to the motion is called rolling friction. It is generally much less than sliding friction. Rolling friction results from the deformation produced where a wheel pushes against the surface on which it rolls. The force of rolling friction varies inversely as the radius of the roller, and it is less the more rigid the surface. The experiment shows that rolling friction is directly proportional to the normal reaction and inversely proportional to the radius of the rolling wheel. Mathematically, rolling friction can be expressed as Fr equal to mu r capital R by small r, where mu r is the coefficient of rolling friction, capital R is the normal reaction, and small r is the radius of rolling wheel. We already have the concepts related to the advantages and disadvantages of friction and how to reduce non-desired frictions. These points are shown here. To summarize, we have discussed physical quantities related to friction, and we have also discussed how we can measure those physical quantities experimentally.